Hi, I'm Evan Hartnett, and this is my Physics 2212 Lab 4 circuits. The purpose of this lab was to use the principles of energy and current conservation to predict the behavior of circuits containing resistors in series and parallel, use multimeters to measure the actual values of the conventional current and potential differences in the circuits, and examine the behavior of ohmic resistors and capacitors. For a brief overview of my results in the experiment, I found that I1 was equal to I2, which was equal to 0.02 amps. I also found my value for the RC to be 5.28262 seconds. The applicable physics principles for this experiment include energy conservation, Kirchhoff's loop rule, current conservation, charge conservation, and definition of steady state, Ohm's law, node rule, potential difference of a capacitor, the RC circuit equation. The assumptions I made in this experiment were that the CCK simulation of circuits is accurate to how physical circuits would function in the real world. For the first part of this experiment, the series circuit, I assumed the system to be the circuit and components, and the surroundings to be everything else. The initial conditions were to create a layout of each circuit according to the lab instructions. The system surroundings and initial conditions were the same throughout the entire experiment, but I'm only listing them here under the series circuit portion of the experiment. The first step was to calculate the expected values of currents I1 and I2 from the two ammeters, which I calculated to be 0.02 amps, and then simulate the circuit in the CCK software and see whether or not this value was the same, which it was, 0.02 amps. Then I replaced one of the ammeters with a voltmeter, leading to the voltmeter reading 3 volts, while the remaining ammeter read 0 amps. This is because the circuit was open, so there was no flow of electrons, and the voltmeter simply shows the potential difference across the batteries and does not equal 0 because the circuit is not completed. I then measured the potential difference for each part of the path around the circuit using the diagram in the bottom right part of the slide. I measured potential differences for each segment along this, and I also created the graph at the bottom left corner of the slide showing how the potential difference changes as you go around the circuit. Then I added an ammeter in parallel to the 100 ohm resistor. This led to both ammeters reading 0.06 amps because the current was able to take an alternate path and go around the 100 ohm resistor. So the current was 0.06 amps as read by the ammeters. I then calculated the resistance of each circuit element, which is shown below in the table. For the RC circuit portion of this experiment, I simulated an RC circuit with a 10 or 20 ohm bulb, 9 volt battery, and 200 millifarad capacitor. I then connected the battery to the 10 ohm and capacitor in series and found that the bulb would brightly illuminate and then quickly dim. I then disconnected the battery and connected the capacitor to the 10 ohm bulb, leading to the same result of the bulb brightly illuminating and then quickly dimming. I then measured the total elapsed time for the 10 ohm and 20 ohm bulbs to charge and discharge, which is shown in the table below. The 20 ohm had about twice the resistance of the 10 ohm bulb and took approximately twice as long to charge and discharge. For the final part of this experiment, the time-dependent voltage across the discharging capacitor, I simulated an RC circuit with a 30 ohm bulb, a 9 volt battery, and a 200 millifarad capacitor. I then measured voltage across the charged capacitor. I then disconnected it from the battery and set the capacitor discharging and plotted 20 seconds of voltage versus time data on a natural log of change in potential over original potential change versus time plot, which is shown in the bottom right corner of the slide. I found the line of best fit for this plot to be negative 0.1893x plus 0.0317 and the value of RC to be negative 1 over the slope of this plot, resulting in a value of 5.28262 seconds for my value of RC. Some sources of error in this experiment were that this experiment was simulated, done entirely online, so real-world conditions may not match the virtual conditions. In addition, some rounding and calculation errors may have been made by Excel. Additionally, I may have had some inaccurate timing when measuring the change in electric potential versus time for the charging/discharging capacitor and data for the ln of change in potential over change in original potential versus time plot. If I was doing this live in real life and used an actual ammeter instead of an ideal simulated ammeter, I would have found the real ammeter would not have displayed 0 ohms for the resistance. A real ammeter would contribute to the total resistance of the circuit. The overall current in the real circuit would be lower than the simulated value from the experiment. If I was doing this live in real life and used a real battery to charge a real capacitor with no resistor in the circuit, I would have found that compared to the simulated model, which would have predicted the capacitor to be charged immediately if there was no resistor, in the real world, all circuit components have some resistance, so it would take time to charge the capacitor.